All right, so for page 2, what we're going to do is we're going to find parametric equations and symmetric equations for lines through the point. So we have point 124 and we have point 143. And what we're going to do is we're going to first find the parametric equations. And so in order to find the parametric equations, we need an initial point, which we have, and we also need a vector. And so here we have our point. And, we'll go ahead and say, this is our sub 0. And we'll just use the first one. So that's going to be 1, 2, 4. And now what we need is we need a vector that's parallel. And so what I'm going to do is I'm just going to find the vector between these 2 points. And so what we're going to have is we're going to have the vector that's the difference between those 2 points. So 1 minus 1, 4 minus 2, and 3 minus 4. And we get that vector, and we're going to get 0, we're going to get 2, and we're going to get negative 1. So there's our vector. We have our initial point, so we can go ahead and find the parametric equation. So for the first one, we're going to have x equals our x value, which is going to be 1 plus 0 t, which is just going to be x equals 1. Our next one, we're going to have y equals, and we have our point, which is going to be at 2 for our y value, and we're going to have add that to our vector times t, and then for z, we're going to have our point, which is going to be at 4 plus in this case minus our vector because it's negative 1t, which is just going to be z equals 4 minus t. All right, so there's all of our parametric equations. And now what we want to do is we want to find the symmetric equations. So when we're doing the symmetric equations, there's a problem. X does not have a t with it for its parametric equation, so therefore we're just going to have x equals 1. That has to be set aside separate because there's no t value. For y equals 2 plus 2t and z equals 4 minus 2t, we're going to have to solve those for t. So we just have to subtract our values with it. Z minus 4 equals negative t, and then we'll divide by our value. So we have y minus 2 divided by 2 equals t, and then we have divide by negative 1, so z minus 4 equals divided by negative 1 equals t. So therefore we can write our symmetric equations to be y minus 2 over 2, and we can write our other equation equal to that because they both equal t to be, and I can go ahead and just use that negative 1 and just say, oh, I have 4 minus z. And there's my symmetric equations. All right, next we want to determine the lines L1 and L2 if they're parallel, skew, or intersecting. And if they intersect, we want to find the point of intersection. So what we want to do first is, distinguish what our vectors are for these lines. Because if the vectors are parallel, then these two lines are going to be parallel. And so, if you recall, our vector is going to just be the denominators. So here we have the denominator a, b, and c. Well, that's going to be my vector that I'm using for my line. So therefore, I have a vector, and I'll call that v sub 1, of 1, negative 1, and 3. And then I have another vector of 2, negative 2, and 7, again, made up from the denominators of because these are symmetric equations. They're all set equal to each other. And I noticed these are not scalar multiples. Again, from section 12.2, we were stated that if two vectors are scalar multiples, then they're going to be parallel. Well, these two vectors are not scalar multiples. Because they're not scalar multiples, what I'm going to do is I'm going to now find all my parametric equations. And so the parametric equation for the first is just going to be x equals 1 times t. Or just x equals t. The next one is going to be y is equal to 1 minus t. And then the next one is just z is equal to 2 plus 3t. It's kind of just like setting all these equal to t and then resolving it, multiplying by the denominator, then adding or subtracting the top. So the next one, I'm going to distinguish that with, I've already used red, so green. And it's going to be x equals 2 plus 2s. So we need a different variable for this because we have two different lines. The next one's going to be y is equal to positive 3 minus 2s. And then the last one is z is equal to 7s. All right. Now, what I have here, I have a bunch of equations that are going to be in two variables, but I also have them equal to the same variable. So what I can say is, I have an equation where I have just t is equal to 2 plus 2s. I have another equation that's going to be 1 minus t is equal to 3 minus 2s. And then I have another equation that's 2 plus 3t is equal to 7s. And so, that's really good because now I have a system of equations in two variables. And I can solve this system to see, is it parallel? Is it skew? Is it, are they intersecting anywhere? And so, because, I have three different lines, they could just be skewed where there's not an intersecting point for all three of these. And so what I'm going to do is I can solve this by elimination, graphing, or substitution. I'm going to go ahead and use substitution. And the reason why I'm using substitution is because I already have a value that's solved. And so what I'm going to do is I'm going to go and set t equals 2 plus 2s into that equation. 1 minus t equals 3 minus 2s, but substituting in what t is. So I have 1 minus 2 plus 2s is equal to 3 minus 2s. And now I'm going to solve for that. So 1 minus 2 minus 2s is equal to 3 minus 2s. Go ahead and cancel out my minus 2s's. And on the left, I'm going to get negative 1. The 2s's are going to cancel out. And so I'm just left with not negative 1 equals 3, but negative 1 equals 3. And so there you see that, well, if my variables cancel out and what I have does not make sense, then I can tell that these lines are skewed. If it did make sense, then I would be able to find, my point of intersection, but I'd have to check it with my last equation to make sure that it would make sense. I'd have to plug in for those two for my values s and t. I'd have to plug those in to make sure that works out. All right, but because negative 1 does not equal 3, it's skewed. And there's an example in your homework where I do one where it actually works out. All right, now the last thing is, we're going to find the equation of a plane. And so a plane in space is determined by a point. So we have an initial point in the plane and a vector n that is orthogonal to the plane. Remember, orthogonal means that it's perpendicular. Now this orthogonal vector we're going to call n, and it's called the normal vector. So anytime you hear the normal vector in, this class, you're going to think of, this is just the vector that's perpendicular to my plane, or perpendicular to, whatever I'm using. And so here's the equation. The equation is n dot r minus r, or the initial r, which is going to be a point, which is equal to 0. All right, and so it's basically just the dot product of of our two vectors that make it up, but one's the initial, and then n is going to be the orthogonal vector, the normal vector. Now, the vector equation of the plane is, we can go ahead and make sure that we do the dot product of both r and r sub 0, and we should get the same thing when we do that compared to n. To obtain a scalar equation for the plane, all we have to do is write this as our normal vector is going to be made up of components a, b, c. Our r vector is our variable vector x, y, z, and our initial r vector is just going to be it can come from an initial point. So r x sub 0, y sub 0 is z 0. And these, why this is a vector, but I say initial point, is because this is going to be a point that is going to come from the origin. So then our vector equation becomes very similar to our line equation, where we have a times x minus x sub 0 plus b times y minus y sub 0 plus c times